Happy Friday, everyone. Welcome back to another Menlo Community Call. I'm Mimi. I'll be your host for today. And as always, if you're in the chat and watching us live, please come say hi. And we've got a nice bit of updates today and a couple of demos that I'm especially looking forward to seeing myself. So if this is your first time joining us, welcome. A quick refresher on how these calls usually work. Each team shares a few things they've been working on during the week, and we stop for a few questions from the chat whenever we can. So for today, first up, we have Yuki with the manual updates. After that, Ariel is going to show a bit of the robot manipulation learning work, and Ashley is taking us on a tour of the mobile app and Asimov Manager. Then Ishnit is walking us through the new VLA and encoder experiments post on the forum, which you should absolutely join, by the way, if you haven't already. And finally, Herman will close us out with our new career opportunities, as always. Okay, so yeah, over to you, Yuki.
Okay, good morning, afternoon, and evening, wherever you are. Hi, I'm Yuki, and I'm actually working on the manuals right now for Asimov 1. So if you guys have been following us for like this whole manual series for the past few weeks, you know that we're working really hard to make sure that Asimov 1, when shipped, can be as easily assembled as possible, right? By providing all the needed, assembly steps and visualization and whatever material we have for you guys. So I want to give a bit of updates on what has been happening last week. This week actually. So we have actually finished the new with us instruction for the pelvis. So now the full pelvis has been documented and visualized so that you can know how you actually assemble each of the parts, all the bolts, where they're supposed to go, and yeah, like even with the motors, how they are being slotted, so on and so forth. So I'm also starting to work on the arm sections. So some of the latest news is that actually after the visits to our manufacturer, we actually have made some change to the part. So expect the visualization assembly here going to be changed also to some of the new parts with better design for thermals, for assembly, and so on. So yeah, it's still a work in progress, but we are getting there soon. We also get like much more practice in how do we create all this visualization. So you can see over here, these are the ARM modules that we are creating assembly for. Yeah, so as you might have noticed, one of the things that we actually added is ability to like add routed wires, right, and cables to tell you like how the cable should go to certain parts. And yeah, so this is the things we have been working on. But I think one of the things I would like to share a bit more about is origami, actually. So what is origami? Origami is an internal tooling that we created specifically for the purpose of creating assembly instruction, right? So the reason why we need to do this is because I am actually not a mechanical engineer and I don't know how to use SolidWorks. So it is actually a bit too complicated for me to learn the whole tool just to create assembly, and it is not really portable over to the web format also, right? So what we actually have to think about is actually what about we create a tools that's easier for us to use, right? Much more friendlier on the web, and we can like just export it directly to the manual afterwards, right? So it's like a smooth I would say pipeline from end to end, from like creating all the animation, visualization, and putting all the parts to the manual itself, right? Yeah. So one of the part that is actually, you can see all of the parts over here. And let's say if I want to, okay, let me change the auto save. I want to like move bolts right to a certain place. I can do that, right? And yeah, so this is all just like tools that is created out of necessity for us to create all the animation, all the steps, placing things in the right place. Some of the things that take deceptively long to make, it's like stupidly so. I spend a lot of time on is actually the wire portion actually. So yeah, so like to creating this sort of like animation and then placing and routing of the wire to be correct. Like even like you can see, right? I want to make sure that like when it route, it's not just like piercing through all the parts. It's actually going to the right hole it need to be, right, and going upward. So yeah, those are like the kind of details that we really pay attention to also. So yeah, so you can see a lot of function here. Right now, it's not really, I would say, ready to be released to the public yet to be used. The reason is because this is very much just for me to work. It's kind of like my own workflow only. So a lot of things has not been ironed out. But we would love to be able to prepare origami for release as an open source project also. So in the futures, if any one of our community members or pre-orders or anyone who own Asimov 1 or even don't need to work on Asimov, right, that want to build, like want to make an assembly manuals or like creating custom instruction or whatever the case is, they can use these tools to just quickly do so and then publish it onto their manuals, docs, or website, and so on. Yeah. So I guess that's all from my side. I hope you guys will like origami when it's come out, and we would love to share more about the process and like when we will get all the new parts updated also. Oh, before I forgot, we also are gonna working on the Asimov OS section soon. So this is actually where our whole software stack is. I know the community has been asking, like, we have all the hardware, so where's the software? Don't worry, we are working really hard on it to package it well, so and then put it in the manual so that you guys can actually all install it and try it out for yourself when you have when we are ready to release all of the components. So I think that's all from my side. Thank you for listening, and feel free to drop any question that you might have. Yeah.
There's a few very excited people in the comments. Do we have an ETA for origami?
Yeah, so I hope we'll be able to release origami as soon as possible. I can always say as soon as possible. The reason why is that like we are spending time to actually create the visualization ourselves. So I didn't really have a lot of time to like touch up on origami and make sure that it's usable outside. Yeah, like we're gonna need a guide and everything to how to use origami also, right? So yeah, definitely working on it. Let's say just put a ballpark of around when Asimov 1 ship, I would say we will probably release origami also. Yeah.
Okay, and I think maybe we can go back on. Maybe you can talk a bit more depth about the changes from the manufacturing.
Yeah, sure. So from the manufacturing side, I think most of the major electrical components will stay roughly the same. I mean, like in terms of like the mechanical structure of it. What does change is a lot of like, okay, I can take examples, right? So what does change is, for example, in this pelvis section over here, instead of like the part that you are seeing right now where it's like solid, it's been converted to like a mesh kind of like design in which it will allow for thermal flow much better from the motors, so it's not don't overheat. And then it's also a lot of decision on like how you might want, like how we might want to like replace some of the square nuts position. I believe in sub-assembly. Yeah, so like here it is. Yeah, some of the square nuts position we might change or might reduce so that like it's easier for you to not have to flailing around with a lot of like falling parts, right? And I think one of the things that we have found that really annoying when we created the when we trying to do assembly is actually this part, right? So you see here there's like 10 square nuts that's supposed to go into the O2B part, but as you can see over here, right, actually nothing is keeping the square nut in place. So what you actually have to do next is like putting a set of like bolts to kind of secure them in place first, right? Before like you can move to the next step, which actually you need to flip it over and then put it on the motors, right? So if you do this without all the bolts, all of the square nut will fall out. Yeah, so like this is the kind of thing that we really trying to perfect to make it easier, yeah, to like assemble essentially. Yeah. But mechanically, not much change. Yeah. I hope that's answered the question.
Okay, thanks, Yuki. Let's move on to Ariel next.
Hello, everyone. Today I will go through our recent work about manipulation with reinforcement learning, and also share a little bit of an article that we will release very soon, like compare and inspirations from walking and locomotion RL to manipulation RL. So this is actually the ultimate task we will be working on. So it's like a flip multiple box with the two arms, and the belt is moving quite fast with 0.1 meters per second. So like the boxes are spawned every 2 seconds roughly. And when we were thinking about this problem, we actually have like different solution to it, right? Like one of it is like VLA and another is RL. So we are trying like different approaches to solve this problem. And I am approaching with the RL solution because I think the scenario is pretty dynamic and it requires pretty fast reactions. This is actually, we've been working like 1 week for it, and this is the initial result for it. So we started with like a relatively simpler task, which it just need to like flip a box and with a moving belt. Actually, this article is also talking about like what can we carry over from locomotion RL, what can we reuse from locomotion, and what needs to be reset, and what are the new troubles or new problems with manipulation, because the two tasks are slightly different essentially. The thing we've been thinking is previously when we're training the flat terrain locomotion, we don't really need vision because we are sending the velocity command, and it's like all the training environment or like deployment environment are with flat terrain, so it doesn't need to really aware of the environment. But which is a bit different from a manipulation case, because for the manipulation, normally you want the robot arm to like interact with the object, which requires you to obtain the object information from the environment, right? So we need to introduce vision in this case, or like most commonly is vision or some LiDAR sensor or something to like obtain like where the object is. So we've been like doing literature review of all this method that involves RGB or visions into our policy. And there are three main approaches that I'd like to briefly talk about, just in case you guys want to try with vision-based manipulation. So like the first is most straightforward thing, that you feed the RGB straightly to RL. Maybe you can add a CNN encoder or some other encoder in the architecture. So it like directly process the RGB camera and also like produce the action during training. So you'll involve the RGB in the RL training loop. But it's actually quite expensive, and putting the images inside the loop will inflate the GPU memory, which really like a limited number you can do the parallel training. And it's really not as training efficient as like just like blind RL policy. So which comes to the second method, which is most commonly used nowadays. It's called teacher-student distillation. So first you train a state-based teacher. What do I mean by state-based? So you don't like actually feed the RGB directly into the policy. Instead, you provide the perfect information of the object from the simulation. Because in Mujoko or Isaac Lab, you can always like extract the information, for example, the position of the box or the orientation of the box into the policy. And you train this policy such that it access to all of this privileged data that you cannot get from reality. Because we just want to train like a teacher policy to do all these tasks successfully. We don't care how much information it has. And then we will, for real deployment, of course, we cannot use this teacher policy because it has too much perfect information that we need to require in reality. So then we distill this with the perfect RL expert trajectory to like a student policy that takes RGB. So it doesn't need to be RL training for the student policy. It's just like basic imitation learning that you feed the RGB and the experts action to the student, and you use the loss as what is the student predicted and what is the real expert actions. And then we can train the student policy that takes the RGB and then produce the same data as what the teacher is producing. And the third method is also being like a lot of people are using it. It's with the modular perception algorithm plus RL. So instead of directly feeding RGB, you can have some algorithms like foundation post, which convert the images to like some perfect information, like the orientations and positions of it, and you feed this as a state information to the RL policy, such that the training is efficient and you, it's like a separate algorithm and thing. But the thing is, sometimes it might not be very reliable. For example, if in your camera there's some occlusion and the algorithm might not be effective, it might like drift it to detect something else, and then your task is really getting confused, and you will produce some very unpredictable actions. So hence we are choosing the second approach to train a perfect teacher expert first, and to distill it to a student policy for like real deployment. Actually, a lot of ideas and architectures are carried over from our previous locomotion training. So the whole architecture and the RL algorithms, which is PPO, is shared. And this is the architecture, which is essentially the same as a initial trial. And also we carry over the idea of using the adversarial motion prior to introduce like a style rewards. So from the previous community call, I think I introduced this method that we find it's pretty hard to like hand tuning with reward functions to get the robot working with a very natural like human-like style. So we introduce AMP to include like a human trajectory we generated from Kimodo, and then it guides the robot to work this way while satisfying all these task rewards. So I like to talk about why we're using it in the manipulation task. So actually, by like 1 week of trying, I would admit that manipulation reward tuning is quite much harder than locomotion reward. Like one reason is there's not that many of open source repo, and all of the manipulation tasks are quite different. You mean like if for walking, every rewards is essentially the same, right? Even if you just walk that way upright and you keep the gait cyclic, and also you keep the feet air time. So the structure is quite same, but for manipulation, the task can be very different. Some are like pick up a box, and some is like peg in a hole, and all this different tasks, and requires very different structures of rewards. So initially I tried by giving some task guidance rewards, which is like let it to approach to the end of the like two sides of the box, because I want to try to let it figure out you should actually grasp the two end and flip it. But based on my experience, it's really hard to make it work, because it might just get confused and you approach it here and it gets a lot of rewards and just stuck here. It's just sort of a hacking instead of actually efficiently grasp it, because it doesn't know, right? You can only encode that much information in reward function. So then I add a little bit of AMP, and I collected some trajectories in simulation. And this is not like real like physics, so the box is like drifting, but it's fine. The only thing we care about is the arm motions. So I collect this trajectory and then convert it to MPZ, which encoded all the joint positions and joint velocities, and as a style reward to guide the arm to do this action. So it actually managed to do it. And also, I realized that it's very easy for a manipulation task to actually hack the rewards compared to locomotion, because locomotion, the scenario is quite strict, right? You either like just walk, or you either just fell down, which will give you like very hard termination. But in manipulation tasks, it's hard to define the termination. You might just stuck there for a long time, but it's hard to detect if you just like stay there to like hack the rewards, or you just actually trying to figure out how to do the task. So it's hard to set the termination. So the task reward we are setting is follow this way. Like first we clear what are the categories we want to set the rewards by reviewing all these papers. So roughly it can be categorized by three. One is task guidance. It's a very dense rewards. Like for example, you can set like a reach rewards based on the distance from your end effector to the goal position. And the closer you're reaching, the more rewards you're getting, right? And milestone rewards is like very sparse rewards. So you only give you the reward once you're reaching a task. Like you flip a box, okay, give you rewards, and that's it. It's a one-time rewards. It's not like accumulated. And also some regularization terms like smoothness and safety. So if the velocity is too high or if the motion is too jerky, you give a penalty to it. So yeah, that's how we essentially set up the rewards to it. And initially, before it flipped the box, we'll get all of this like reaching dense rewards. And after the pulse, you finish the flipped. After you're getting the flipped milestone, you will not be able to get all of the rewards beforehand. Otherwise, you would just reward hacking stay there, right? And after this, you will be having some other task. For example, like stable release. After flip it, how do you manage to like release it to make sure the box is still in the belt and instead of like damaging it and something like that. And also like hard failure, because sometimes it just crash with the belt and we need to penalize it. And we also got some initial results for the student policy distillation. And this is the camera. It's 96 by 96, so it's not as like high resolution as the traditional ResNet is using, but we just as an initial trial, and this is much cheaper to train. So yeah, we have two cameras in the training. So one is the front cameras to capture the arms and the box, and one is like a top cameras to capture the whole belt and the box. And this is the distillation results. So you only access to the RGB frames and the robot state data, like the drawing encoders and everything. And it's actually able to do the same thing that the expert is doing, which is quite surprising. Yeah, and I guess the next goal, which we'll probably do maybe start next week to deploy this in real, and this might also help us finding out all of the problems that to deploy in real, like all this noise, sensor noise that we didn't put in enough so that it doesn't really work in real. So yeah, that's our goal next. Yeah, I'll stop from here. We will release this article very soon, so you guys can all give it a read.
Thanks, Ash. Thanks, Ariel. Sorry. There's a few questions for you in the comments. I'll just flash them on the screen. There's a question from Jack Ironside.
As far as I know, random forest is more for classification task, right? So I don't think it can be work on such, high dimensional control problems. Yeah, so normally I think for manipulation or control, it's mostly either imitation learning or RL or VLA, or some like visual algorithm to IK. Yeah.
Okay, next question.
Oh, actually, it's not. This is not encoded in the reward function. For like the potential error is normally encoded in the domain randomization, which means you randomize the errors and things in a certain like realistic range, and then you train with it such that in any cases you have to do this anyways. So yeah, that's it. But still, calibration is very important. So we're trying to like make it perfect. But if we cannot fill the little bit of gap that we cannot solve, we'll introduce the domain randomization. Yeah. So if you train with like unperfect data, so you will be able to adapt it to unperfect data in real. If that answers your question.
Okay, thanks, Ariel. If there's no more questions for Ariel, we'll just move on to Ashley next.
Yes. Okay, let me share my screen. Okay, hi everyone. I'm actually the product designer here at Menlo. So for today, I'm going to walk you through the mobile app experience with our latest update. So there's still a lot of work to do because you will see like some placeholder copy and a few things that will definitely change in the future. But what I want to show you today is the experience, like the shape, the flow, and how it feels. Okay, so on the first launch, there's one sign button, like the standard sign and sign up flow. And then before you can do anything, it will ask you to like create a recovery passphrase. So Menlo cannot like reset or recover this passphrase. If you lose this passphrase and all of your devices, there's no support ticket that brings it back. And I feel like that's honestly like the price of the robot that not trusting the cloud. However, we feel like this could be a bad UX for the user. So we're currently working on like a better approach for this. Let me try to create a recovery passphrase. It's gonna take a while because like I run a lot of things on my computer right now. Okay, so once you're in, the first thing you see is the My Robot screen. So up here we have like the try it out sections. Anyone can jump in and then drive a virtual robot in the cloud right now. The same cockpit as the real one, no hardware required. And then the grid below, you can see like the area that's gonna show you your robots that you have connected to the mobile app. So let me walk through the flow of pairing of robot with a mobile app right now. Also on the first pairing screen, you will see like the tab of hardware, since we are going to have like different type of robot in the future. And for the current mobile work, we mock and tested 2 types of hardware, which is our pipetto robots and the micro factory ones. So let's go with the pipetto robot for now. So on the second screen, we will like give you the guides for you to turn on the pairing functions on the hardware, because like the content is just a placeholder for now, but it will be rewritten based on the exact type of hardware you chose. And then just like turn on pairing on my robot. And then it will start scanning and everything, like just phone to robot over Bluetooth. And then you will select the robot. And it will ask you to verify the code. So the font shows like 6 characters and the robot shows like the same 6 character on its screen. So that's how we stopped a man in the middle, because the code is built from both side keys. So it's never sent over the air. The only thing that connects the 2 screens is your eyeballs. So if they don't match, you can just like click on they don't match. And then the whole thing shut down. But let's not do that for now. And then your robot is connected to your mobile app. Okay, so let's go back to my robot page. So now we have the robot. Let's try to drive it. So a few things happened. So the cloud double checks if I'm actually allowed to drive this specific robot. And then it will spin up like a live video room, and then the robot jumps from its side. Like you can see like the camera is up for like about like 2 seconds. I'm using the mod right now, so you may not like see like the actual camera fit for sure. So before you can drive the robot, you will have to like make sure that everything is safe, because this is the real robot and with real surroundings. So once I click like how to start driving, yeah, and then now the robot is live. So this is the cockpit for a bipedal robot. So for the micro factory one, it might look a little bit different for UX. So the whole screen is like the live camera, and you're basically looking through the robot eyes. So across the top, you can see things like latency, that you can know how fresh the link is. And we have like the speed chip and the poster that you know the robot state. Okay, so when you tap on this bill, you can actually dim and shut down the robot, and you have to make sure that the robot is physically supported. And then below here, we have like the driving sections. So I did it in the controller style. So we have like 2 paths. The one on the left is for drive, like forward, backward, and then drive to side. And then the one on the right is for turn, rotate in place. So they are like spring loaded. So once you let go and the robot stops every time. So right in the middle, we have like the stop buttons. So this is like a sub pause, because it would just like zero all of the robot speed and freezes the input, so you can take your thumbs up safely. 2 more things is that you can switch between the joystick and buttons, depends on which one you prefer. And you can also like rotate to landscape mode. So it will go like fully immersive. Okay, so this is the cockpit for the bipedal robot. I also want to show the UX of the microfactory one because it's a little bit different. Actually, but first, let me change to that mode so you can see how that mode looks like. You know, our microfactory is this is like a 2-arm robots that you're not steering it anywhere. You're just using it like a pair of hands that you can pick something up. Okay, so similarly to the bipedal cockpit, you have to like make sure everything is safe before you control the hardware. So there are 2 ways to fly the arms, which is the joystick and the motions ones. So for the joystick, each arm will get its own stick. So the left stick fly the left hand and the right stick with the right hand. So I can work like with both at once. I just push the stick and then the hand slide across the bench. That's moving it on the flat. Okay, so to lift the hand up and down, I drag with 2 fingers. Right now I'm using like a computer mouse, so I cannot do that. But you get the idea. So actually, like grab something, I will hold to the grip, and then for that arm and the hand, just like closes around the objects. And the second I let go of the stick, I'm just like hold in the air, stop that, and waist right where it is. So I can like positions one hand, park it, and then go work with the other. And for the motions UX, this one, I actually love this one more, but so for this one, so it will act like my phone basically becomes like a robot's hand. So I hold the arm follow buttons, and then I just move the phone through the air. I push forward, and then the arm reaches forward. I tilt it, and then the wrist tilted. So it copies whatever my hand does. And if I'm lifting something big that need both hands, I'm just holding both buttons and move the phone, and both arms will come together with me. So once you let go, they would just freeze right there in the air. And of course, at any point, you can just like stop. It will freeze both arms holding their pose. Yeah, I think that's everything for the cockpit experience. Other than that, we have like some other standard settings which are not fixed yet. Lots of things gonna change in the future, so I'm not going into details for this right now. So everything so far is just like on the phone side. I want to share like how it looks like on the robot side of things. Okay, so there's like 2 programs running on the robot's little pie. One is called the Asimov Edge. You can think of it like a brand name, and then it does like Bluetooth pairing. It checks every command, and then it streams the camera. It talks to the motors. And then this one is actually the Asimov Manager, which is I would say like the supervisor. So I guess the easiest way to think about it is like it's the robot router admin page. So let me just go straight down from the left sidebar so you can see like the whole surface. So let me get the robot ready so you can see like the actual states. So we have like at the top we have overview, so which is the robot dashboard. So at one glance, it will tell you like what is online and every part is whether every part is healthy, and there's also like a quick start, quick restart if you want to restart anything. And then we have like the first category, which is the connections category. So we have like all of the standard things like Wi-Fi, exactly what it sounds like. And then we have remote access. It will reach the same admin page when you're not on the robot network for remote support. And then we have the Menlo Cloud. This is the important one because it's the single switch that turn the robot at our platform. So that's what makes the robot show up in our app and be drivable. And then we have controller. This is the robot ends up pairing I presented during the mobile app walkthrough earlier. So on the headless robot, This page basically is the robot screen, so you can compare the code when pairing the robot with a mobile app. And then for a second category, we have system recordings with captures of the teleop sessions, and you can optionally upload them to Menlo Cloud. And then we have software, every background service of software. This is where the Asimov Edge gets turned on. And then we also have like hardware where so for robot setup, it's basically what it says. You can set up the newly built robot motors from here. And also the firmware, which like the real-time firmware that actually drive the motors. Plus the link to the robot control unit. And then for the last category is the advanced group. We have advanced settings. Basically every raw settings in one place. One config file is like the source of truth. You hit like apply, and then it will rebuild the entire Edge runtime from it. And then we have troubleshoot, super standard, one page that checks every run and then show recent logs. Also, and to make sure that everyone knows what they're doing, they're also like a very friendly onboarding to guide you like the whole process of setting up the robots, hardware and software as well. Yeah, I guess that's everything on my end. If there's any comments or feedbacks or any concerns, please comment directly. Thank you.
That's amazing, Ashley. I think our whole team is really excited with Ashley's work. It's so good. Okay. I hope everyone enjoyed the tour. If you guys want to comment or say anything, just drop in the comments or leave us comments on Discord as well. And then next up, we'll move on to Ishneet. Thank you, Ashley.
Yeah, so today I'll over the last few weeks here sort of discuss around Kepler, what VLAs you're trying to train in simulation and deploy in real. And then this week we did some mini experiments to actually understand more on the encoder side for the VLAs and actually try to understand why we need to supply so much data and so much variance in data initially to actually get the VLA to train robustly. And if we don't do that, then the VLAs are actually quite brittle. And if you change the camera angle at deployment slightly, you realize that the VLA won't generalize. And so what we found out this week was that VLAs are quite viewpoint brittle and they don't generalize very well to different viewpoints. And that could be a function of the action encoder is cheating, or it could be a function of the vision encoder is just too good that it's able to detect every small change in camera angles. And so actually you might have to supply like too much data for it to generalize, which also doesn't make sense and it wouldn't be the most data efficient approach. So the main argument we present in this small write-up is that moving the camera changes the vision's encoder's output more than moving every object on the table. So you would imagine if I give the VLA or if I give the vision encoder a totally new scene and a totally new camera angle, that would make sense if it can't generalize. But if the same scene, I just change the camera angle by 2 degrees or just move it slightly, you would assume it should still be able to generalize. And it should be at least robust to like these small nudges in the testing setup if at deployment it changes. But we actually realized that these small angles have basically almost the same effect as like a totally new scene. And we realize that this is not a recognition failure because the objects are still found across views, but it's more of that the viewpoint is encoded inside every patch token, and underneath the content is just very sensitive to the viewpoint and the camera angle because every pixel will just change if you change the camera angle even so slightly. And so the main problem we're trying to investigate is that VLAs handle object positions they have never seen, and then they fail when the camera moves. And so in practice, this means adjusting camera mounts. You have to just keep adjusting camera mounts until the policy works. And it happens in sim and on real data, and then viewpoint augmentation doesn't remove it. And because the vision encoder is pre-trained and mostly frozen, the question is, how does the problem even begin? So the simple test we did was we built image pairs where the embedding should be nearly identical and measured them. So the test we're running right now is that we have 18 photos, and the way we organize the photos is we have like 3 objects and we have multiple different camera views over here. And so how we organize the photos is that we have 3 pair types where we have objects moving with the same camera. So that would be like, um, so you have camera A. This is the same camera, but you have objects moving in this same orientation. And then the second pair would be you have the same layout, but scattered across different cameras. And then the third one would be you just have both changing. So you have like around 18 pairs for the same camera. You have like 45 pairs for the camera moving, but the objects being in the same position. And then when you change both, you have like 90 pairs. So we ran vision encode experiments on all of these pairs to actually understand and get some better intuition into how the vision encoder is actually performing. And so the 4 encoders we tested on, which are over here, the 4 encoders we tested on are all at 224 pixels. So we test the SIGLIP SO400, which was used in Pi0. We also test the SIGLIP 2, which was used in Groot N1. And then we test Dino V2 VIT, which was used in OpenVLA. And then we just also test a clip VIT. And the metric we're actually measuring is the mean cosine distance between tokens at the same index of the 16 by 16 patch grid. And so that grid is the actual visual state that the language model will actually consume in the form of like embeddings consecutively. And just for like a control experiment for scale, a 10% brightness change in the camera or in the photo would score like 0.05 on SIGLIP and 0.001 on Dino. So that actually means that if you just increase the brightness, you won't actually find a big difference. So that's just like a control experiment. And so these are the main results we got, was that the camera changes the state more than the world does. And the 2 points to take note from here is that the ratio is above 1 in every encoder, and that camera only is within a few percent of camera plus layout. So once the viewpoint shifts, rearranging the objects adds almost nothing. So you're almost, even when you're supplying data where you're putting a lot of different objects versus just changing the camera angle, actually it's not allowing the model to learn more robustly because it's doing the same effect. And the distance matrix over here, which is the 3 6x6 blocks on the diagonal, it shows the results without averaging, and the light stripes are actually the object rearrangements, and the dark blocks are the camera changes. And so these ranges of the different camera views, they actually overlap at the extreme. So the smallest camera move, which would be the adjacent side views from like E to F, they scope below the largest rearrangement, and the distance tracks how much actually the image changed. And a camera move changes all of it, while a layout change only changes part of it. And so this shows us that this is the mechanism of the vision encoder and not a flaw in the test. And also to prove that the objects are actually never lost when we go across different camera frames or change the camera angle slightly, is that we thought that maybe it's the encoder cannot track the objects across views, but it should be, of course, it should be able to do it because these encoders have been for a long time. They've actually been quite robust in vision-based tasks, detection, tracking objects across frames. And so when we cluster all the patch tokens with k-means, and then we paint the clusters back, it shows the same content clusters. We are able to still find the joystick. We're able to find the foot. So we're still able to track objects across frames. So that's not the issue. And then if we go to this section where does the viewpoint actually hide? And so we realize that for each patch, if we ask every image for its nearest neighbor, we realize that the viewpoint actually sits within the token. So because the objects are recognized, the camera pulls harder, and then each patch feature is just coarsely inside the token. So this means that the vision encoders still are able to track objects across frames, but it's just that they are really sensitive to a single change in the camera angle because the vision encoders were never trained to be robust for like VLAs. The vision encoders were trained to really just be really sensitive to any change in the camera. So we actually need to think through how we'll solve this problem. Is it at the action head, or is it actually making the vision encoder sort of dumber where you don't want it to actually track such minute changes because you won't be able to supply enough data for the model to generalize. So overall, the conclusion for what this small experiment means for the policy is that the policy state is that token grid. And because camera pose is its largest coordinate, a viewpoint change moves the state further than any object rearrangement into the region that the action had never mapped. And so the likely reason it never mapped is its coverage. On a single rig, if you're just collecting data, placements vary across thousands of demo and the camera doesn't move at all. And so the information needed to recognize the same scene at a different view is in the token, and there's little pressure to use it. So this part is and we were able to actually validate this across different types of encoders as well. So we actually tried a geometric encoder to actually see if maybe the vision encoders were just not good enough. And so we actually did the same probe on VGGT and VGGT omega, and we realized that the geometrical encoder is slightly better at it because the VGGT omega is actually able to be more robust to it, and it doesn't actually change the latent distance as much across camera views, but the same problem still arises even for VGGT. So we realized that it's more of what these vision encoders are actually trained for compared to like what a VLA actually requires. And so what we realize is the next steps to run would be like, one, we could scramble the conditioning tokens. So we fix camera and objects, and then we inject noise into the conditioning tokens. You keep the bad failures, and then you inspect which tokens were corrupted. And this will actually show that the representation moves, and we will be able to verify if the policy depends on the part that moves. And it also separates the two hypotheses that if the calibration is memorized at specific token positions by the action head, the damage will be localized. But if the camera signal is spread across all 256 tokens, then the dependence will be diffused. And then we can also try other things like quantizing the patch latents. So it will actually collapse near identical features onto the same code, which should remove the fine camera detail and still keep the coarse content. So these were some experiments we ran this week. And we're continuing to read more papers, equipping ourselves with more information about what other people have done and making sure we really have a more holistic understanding of this problem. And if you guys you have any ideas on these experiments, you just comment down in the forum post, so you can create your own forum post. All this code is open source. It's in a branch in a world encoder repo. So if you guys want to contribute, or if you want to do some experiments, or just understand what we were doing, you should be more than you should feel free to do it. Yeah, I think that's all from my side for today.
Okay, thanks, Ishneet. Shall we move on to Herman next in the interest of time?
Yep. Hi everyone. I'm Herman. Nice to see you guys again. So we've got like a new role that we've recently posted. So I just wanted to dive into it real quick because this is something new for all of us. Yeah. So we are looking for developer relations who will potentially be the public face of Asimov in the builder community. So this requires a lot of evangelism, also some form of hardware skills. So if this sounds like you, please apply for it. I'm looking forward to meet you and talk to you as well. This role is based in the US, so if this kind of fits you, feel free to apply and let's have a chat. I would also like to share that this upcoming Tuesday, 11 August in Singapore, we'll be having our Singapore AI and Robotics Demo Night. We've got lots of speakers lined up for you. Salim will be there. Alejandro and Jashan from the Menlo team will be there as well. I look forward to meeting you guys in person. If you guys do happen to stop by, then let's have a chat. Thank you.
Thanks, Herman. Okay, so I think that's a wrap for today. Today has been a bit of a longer session. I hope everyone enjoyed it. And I really appreciate everyone who joined live and everyone watching the replay later. If you enjoyed the stream, subscribe so you don't miss out the next one. Join our Discord forum, follow us on X, all of that. And yeah, see you all next Friday. Bye.